we find ourselves in the company of distances so immense that even light, the swift messenger of the universe, must spend ages crossing them. There is no need to hurry across those distances. The stars themselves have never been in a hurry. They have spent millions and billions of years quietly carrying out the patient work of shining, warming, and slowly changing, one moment blending almost imperceptibly into the next. If you imagine standing beneath a clear night sky, far from city lights, you might notice how peaceful the stars appear. They do not reveal the restless activity hidden within them. Deep inside every bright point overhead, atoms gently press together under extraordinary pressure, releasing energy that travels outward through layers of glowing gas before finally beginning its long journey across space. By the time that light reaches your eyes, the moment that created it has already become part of history. This quiet delay belongs to nearly everything in astronomy. We never truly see the universe as it is now. We see countless versions of its past arriving together, each beam of light carrying a different age. A nearby star may appear almost as it looked a few years ago. A distant galaxy offers a portrait from millions of years before the first humans walked across Earth. Looking upward is also looking backward, and the night sky becomes something like a vast library whose shelves are arranged not by place, but by time. There's something calming in this realization. While our daily lives often encourage immediate answers and rapid movement, the universe continues to unfold according to rhythms that cannot be hurried. Entire civilizations might rise and fade during the briefest chapter of a star's life. Mountains slowly weather into valleys, while galaxies quietly complete only a small fraction of their graceful rotations. Elsewhere, beyond the familiar constellations, clouds of gas drift through darkness so gently that their movements would seem almost motionless to us. These immense nebulae are among the coldest and quietest places where new stars may eventually begin. A slight increase in density, perhaps encouraged by the distant passage of another cloud or the fading ripple from an ancient stellar explosion, can slowly allow gravity to gather matter together. Gravity is remarkably patient. Unlike storms or earthquakes, it does not arrive suddenly. It simply continues pulling, hour after hour, century after century, never becoming tired. Over hundreds of thousands of years, then millions more, a faint concentration of hydrogen grows gradually denser. The cloud contracts almost without sound, although sound itself cannot travel through the emptiness surrounding it. As the cloud becomes smaller, its center grows warmer. Molecules move more quickly. Pressure quietly builds. Eventually, if enough material has gathered, temperatures become high enough for nuclear fusion to begin. A new star opens its eyes to the universe without celebration or announcement. There is no applause in space. Only another gentle light begins shining among countless others. Our own sun experienced such a beginning roughly 4.5 billion years ago, before Earth possessed oceans or continents, before the moon circled overhead, before the first tiny cells appeared in ancient seas, our star emerged from one small region within an enormous molecular cloud. The material that once drifted through interstellar darkness slowly became the source of every sunrise humanity has ever known. Around the young sun, countless grains of dust circled through a flattened disk. Tiny particles bumped together, sometimes sticking, sometimes drifting apart again. Over immense stretches of time, these grains became pebbles, then rocks, then objects large enough for their own gravity to gather still more material. Piece by piece, almost unnoticed against the backdrop of cosmic time, planets formed. It is comforting to remember that worlds are not built in an instant. They are assembled gradually, through countless quiet encounters. Even something as solid beneath our feet as Earth began as drifting dust, carried patiently around a young star whose light had only recently begun its long existence. Meanwhile, the universe itself continued expanding. This expansion is one of the most extraordinary discoveries ever made, yet its effects are surprisingly gentle. Galaxies are not rushing through space like sparks from a fire. Instead, the space between distant galaxies slowly stretches, carrying them farther apart as the fabric of the universe gradually grows. Imagine tiny marks drawn upon the surface of an inflating balloon. As the balloon expands, every mark sees the others becoming more distant, not because they are moving across the surface themselves, but because the surface itself is growing. The universe behaves in a somewhat similar way, although in far more dimensions and with complexities beyond the simple image. For billions of years, this quiet expansion has continued without pause. Entire clusters of galaxies drift farther from one another, so slowly that no single generation could ever notice the change directly. Yet, over unimaginable spans of time, those small differences accumulate into profound transformations. One day, observers living in a distant future may find that many of today's galaxies have disappeared beyond the limits of visibility. Their light will take so long to arrive that it never reaches them at all. The universe, from their perspective, will seem smaller, not because less exists, but because more has quietly slipped beyond observation. There is a certain gentleness in this thought. Things are not always lost through sudden endings. Sometimes they simply become too distant to see, continuing their own quiet stories far beyond our horizon. Back on Earth, long before astronomers understood cosmic expansion, people looked upward with different questions. Ancient observers noticed the dependable return of seasons, the slow wandering of planets, and the steady appearance of familiar constellations. Without telescopes, they still recognized that the heavens possessed remarkable order. Stone circles, temple alignments, carefully carved observatories, and generations of oral tradition all reveal the same enduring curiosity. Across cultures separated by oceans and thousands of years, human beings lifted their eyes toward the same stars. The names differed. The stories changed. Yet the quiet habit of wondering remained constant. Curiosity itself may be one of humanity's oldest companions, Even when answers were incomplete, the act of asking connected people to something larger than themselves. Sitting beneath a clear sky required very little. A calm evening, a patient gaze, a willingness to notice. Modern science has transformed many mysteries into measurable questions. We now understand that stars are made mostly of hydrogen and helium. We can calculate their temperatures, estimate their ages, and observe planets orbiting distant suns. Yet, every new discovery gently reveals still more questions waiting beyond it. Scientists continue investigating the nature of dark matter, an invisible substance whose gravity helps shape galaxies. Current evidence suggests that ordinary atoms account for only a small portion of everything that exists. Most of the universe remains hidden in forms we do not yet fully understand. This uncertainty is not a failure of science. It is one of its quiet strengths. Science does not promise complete certainty. Instead, it patiently improves its understanding, allowing observations to reshape ideas whenever new evidence appears. Like rivers gradually carving valleys through stone, knowledge often advances by slow persistence rather than dramatic leaps. Meanwhile, stars continue living their patient lives. A star spends most of its existence quietly balancing two opposing forces. Gravity constantly pulls inward, trying to compress the star into a smaller sphere. Fusion within its core releases energy that pushes outward. For millions or billions of years, these forces remain in remarkable balance, allowing the star to shine with steady brilliance. Our sun has maintained this equilibrium for nearly half its lifetime. Every second, hundreds of millions of tons of hydrogen become helium within its core. Although this number sounds enormous, the sun contains so much material that it can continue this process for roughly another 5 billion years. 5 billion years. It is a length of time so vast that language struggles to hold it comfortably. Entire branches of life will appear and disappear. Continents will slowly drift into unfamiliar shapes. Mountain ranges will rise, erode, and rise again elsewhere. Oceans may open and close as Earth's surface quietly reshapes itself. Through much of this unimaginable future, sunlight will continue arriving each morning, crossing nearly 150 million kilometers of space in about 8 minutes before gently touching Earth's surface. That familiar warmth on your skin began its journey long before you noticed it. Even more remarkably, the energy within that sunlight began much earlier still. Photons produced deep inside the sun can spend thousands or even hundreds of thousands of years, gradually working their way outward through dense layers of hot plasma before finally escaping into open space. The sunlight reaching Earth today carries with it an astonishing history hidden inside every beam. Nature often works this way. The simplest experiences sometimes arise from the longest stories. A quiet breeze crossing a field may owe its existence to sunlight warming distant air hours earlier. A forest grows from seeds that waited patiently beneath soil through changing seasons. Snow resting peacefully upon a mountain preserves tiny records of climates from years gone by. The universe seems especially fond of long preparations. Nothing about its greatest structures appears rushed. Galaxies rotate slowly enough that individual stars require hundreds of millions of years to complete a single orbit around their centers. Spiral arms seem frozen when viewed across human lifetimes, yet they remain in constant, graceful motion. Billions of stars follow gentle paths determined by gravity, each orbit contributing to a pattern too slow for ordinary eyes to witness directly. If time itself could somehow be accelerated until millions of years passed like seconds, the galaxy might resemble an elegant whirlpool of light. Clouds would gather and disperse. Bright blue stars would briefly appear before fading. Dark lanes of dust would drift like soft currents through luminous rivers of countless suns. Instead, we experience only a single still frame within that immense dance. Perhaps that is enough. There is peace in knowing that movement need not always be visible to be real. The oldest trees continue growing even when their change escapes daily notice. Ice slowly reshapes mountains grain by grain. The stars themselves remind us that patience is not merely waiting. It is the quiet unfolding of processes too vast to hurry. And somewhere, far beyond our own galaxy, countless other stars are beginning their own long journeys, adding their gentle light to a universe that has always preferred the language of slow beginnings. Far beyond the quiet spiral of our own galaxy, other islands of stars continue their patient existence, separated by expanses of darkness so large that ordinary distances begin to lose their meaning. Between galaxies, there is not complete emptiness, but rather a delicate scattering of lonely atoms, faint radiation, wandering particles, and the subtle geometry of space itself. Even what we often call empty space possesses its own quiet character. If one could somehow drift through the vast region between galaxies, there would be almost nothing familiar to mark the passage of time. No nearby stars would brighten the darkness. No planets would circle overhead. The nearest galaxy might appear only as a faint, mist-like glow, suspended against an endless black background. It would not feel lonely in the ordinary human sense. It would simply be still. Stillness, after all, is one of the oldest conditions in the universe. Although the cosmos has always been changing, many of its changes occur so gradually that stillness becomes the experience of anyone living within them. Entire civilizations may pass unnoticed, while two galaxies move only a fraction closer together. A single star may shine with nearly identical brightness for hundreds of millions of years. The universe reminds us again and again that profound change often wears the appearance of calm. Our own galaxy, the Milky Way, contains hundreds of billions of stars. They are not scattered randomly, but arranged within graceful spiral arms, rich with gas and dust. Between these arms lie quieter regions where older stars continue their steady orbits around the galactic center. Our sun happens to reside in one of these relatively peaceful neighborhoods, far enough from the crowded center to enjoy long periods of stability. The center of the Milky Way is home to something remarkable. There, surrounded by millions of tightly packed stars, rests a supermassive black hole known as Sagittarius A. Although black holes are often imagined as endlessly consuming everything nearby, reality is much quieter. Sagittarius A spends much of its time surprisingly calm, drawing in only small amounts of surrounding material. Even objects famous for their immense gravity are governed by patience. A black hole does not reach across the galaxy to gather distant stars. It influences its surroundings through the same gravitational laws that guide planets around the sun. A star passing safely far away continues along its orbit, almost undisturbed, just as Earth peacefully circles our own star year after year. The extraordinary often turns out to be quietly ordinary once we understand it. Scientists first predicted black holes through mathematics, long before observing convincing evidence for their existence. Equations describing gravity suggested that enough mass compressed into a small region would create a boundary beyond which even light could not escape. At first, this seemed almost too strange to accept. Yet nature has repeatedly shown that our intuition is not always the best guide across cosmic scales. Today, observations of stars orbiting the center of our galaxy provide strong evidence for the presence of that hidden mass. Their graceful paths reveal an invisible companion whose gravity quietly shapes their movements. The black hole itself remains dark, but its influence becomes visible through everything around it. Sometimes the universe is understood not by what we see directly, but by the gentle patterns left behind. A similar lesson appears throughout science. We cannot see the wind itself, yet we watch leaves sway in quiet forests. We cannot observe gravity as a substance flowing through space, yet planets remain faithfully in orbit. We cannot touch time, yet we notice its patient work in growing trees, weathered stones, and the changing faces of distant stars. Nature often speaks through consequences rather than appearances. Meanwhile, another enormous galaxy slowly approaches our own. The Andromeda Galaxy, our nearest large galactic neighbor, lies about 2.5 million light years away. At first glance, this seems unimaginably distant, and by everyday standards it certainly is. Yet, on the scale of the universe, Andromeda is close enough for gravity to have slowly drawn it toward us for billions of years. Its journey is gentle. Although the two galaxies move toward one another at hundreds of kilometers each second, the immense distances involved mean that the encounter will not occur for roughly another 4 to 5 billion years. Even then, the word collision can be misleading. Individual stars are separated by such extraordinary distances that direct impacts between them remain extremely unlikely. Instead, the galaxies will slowly pass through one another like two vast clouds of drifting fireflies. Gravity will reshape their elegant spiral structures into something new. Streams of stars may stretch into graceful arcs across space. Clouds of gas will meet and gently compress, encouraging fresh generations of stars to form. After many hundreds of millions of years, the two galaxies will settle into a larger, calmer galaxy, unlike either of their original forms. It is less an explosion than a long conversation conducted through gravity. If observers existed somewhere within that distant future, they would witness magnificent skies unlike anything we know today. Bright rivers of stars would fill the heavens. Familiar constellations would disappear as stellar neighborhoods slowly rearranged themselves. Yet, for any individual living through those ages, each night's changes would remain almost imperceptible. Even the grandest transformations arrive one quiet evening at a time. Elsewhere across the universe, many galaxies have already completed similar mergers. Astronomers observe enormous elliptical galaxies whose smooth shapes hint at ancient encounters now long finished. The evidence remains written across the distribution of their stars, preserving history's billions of years old. The universe rarely erases its memories completely. Ancient light continues traveling. Old stars continue shining. Gravity continues tracing invisible paths. Everywhere we look, the past gently accompanies the present. Closer to home, small icy worlds drift through the distant outskirts of our solar system. Beyond the orbit of Neptune stretches the Kuiper Belt, a broad region populated by frozen remnants left over from the birth of the planets. Even farther away lies the hypothesized Oort cloud, an enormous spherical reservoir of icy bodies extending perhaps a light year from the sun. If the Oort cloud exists, as current evidence suggests, it represents one of the largest structures belonging to our solar system. Its countless icy objects spend millions of years following slow orbits through profound darkness. Occasionally, the gentle gravitational influence of a passing star or the tidal pull of our galaxy nudges one of these frozen travelers inward. After an unimaginably long journey, it may become a comet, developing a luminous tail as sunlight warms ancient ice that has remained undisturbed since the earliest days of the solar system. A comet is, in some sense, a visitor carrying memories from another age. Within its frozen layers are materials older than Earth itself, preserved through billions of years of quiet cold. Each passage near the sun briefly awakens these ancient travelers before they return once again to the distant darkness from which they came. There's something deeply peaceful about this rhythm. Long periods of silence, a brief encounter with warmth and light, then another long return into stillness. Nature seems comfortable with such long cycles. On Earth, we often measure time through days, seasons, and years. Trees mark their age through rings hidden beneath bark. Rivers slowly reshape valleys over thousands of years. Glaciers advance and retreat across mountain landscapes through changing climates. These rhythms already feel spacious compared to our daily routines. Yet astronomy gently extends our imagination further still. Stars age over billions of years. Galaxies evolve across tens of billions. The universe itself measures its history in spans that challenge every ordinary intuition. And still, none of these immense processes appear hurried. Even the eventual end of stars usually arrives gradually. Our own sun, for example, will not suddenly cease shining. As hydrogen in its core slowly becomes depleted, the balance between gravity and fusion will gradually change. The core will contract, temperatures will increase, layers surrounding the core will respond in complex ways that astronomers have modeled through decades of careful observation and theory. Over immense stretches of time, the sun will become brighter. This increase is already happening, though so slowly that it remains invisible across human history. Hundreds of millions of years pass before the change becomes significant. Oceans, climates, and eventually Earth's surface itself will slowly respond to the increasing warmth. These changes belong to futures so distant that they almost become another universe entirely. It can be strangely comforting to recognize just how much time lies between now and then. Human history occupies only the thinnest layer upon that immense timeline. Every language ever spoken, every city ever built, every poem, every telescope, every voyage across every ocean. Together, they fill only a tiny moment within the life of one ordinary star. Yet that brief moment has allowed the universe to become aware of itself in remarkable ways. Atoms forged inside long-vanished stars eventually became oceans, forests, mountains, living cells, curious minds, and quiet evenings beneath the night sky. The same physical laws governing distant galaxies also govern the gentle beating of a human heart. There is no sharp boundary separating us from the cosmos. We are one expression of its long history. The calcium within our bones, the oxygen we breathe, the iron carried through our blood, all were created inside stars that completed their own lives billions of years before the sun was born. Their gentle endings scattered new elements across space, allowing future generations of stars and planets to form from enriched clouds of gas. In this way, every ending quietly becomes another beginning. The universe has repeated this patient cycle for billions of years. Stars form, stars shine, stars slowly change, stars return their material to space, new stars emerge. The rhythm continues. Perhaps that gentle repetition is one of the deepest comforts astronomy offers. Nothing truly stands apart from the larger story. Every particle participates in cycles extending far beyond any single lifetime. And as the night grows quieter and the imagined stars continue their slow journeys overhead, the universe asks for nothing from us except the same patient attention it has always rewarded with wonder, one peaceful moment after another. Beyond the lives of individual stars, the universe continues its quiet habit of arranging matter into patterns that are both graceful and immense. If we could travel far enough away from the Milky Way and look back from a great distance, we would not simply see isolated galaxies scattered at random. Instead, we would begin to notice something more delicate. Galaxies gather together. Some belong to small groups of only a few companions. Others collect into clusters containing hundreds or even thousands of galaxies, each one carrying billions of stars through the darkness. Between these clusters stretch long filaments, subtle bridges of galaxies, and invisible matter extending across hundreds of millions of light years. Together they form what astronomers call the cosmic web. It is a fitting name. Seen through careful computer simulations and deep astronomical surveys, the large-scale universe resembles an intricate network of luminous threads surrounding enormous regions where comparatively few galaxies reside. These vast, empty spaces, known as cosmic voids, are among the quietest places imaginable. A void is not entirely empty. There may still be isolated galaxies drifting through its immense volume, along with sparse clouds of gas and the ever-present background radiation left from the universe's earliest moments. Yet compared with the rich clusters nearby, these regions feel almost like long pauses between chapters. Silence, it seems, exists even on the largest scales. The cosmic web itself did not appear all at once. Current evidence suggests that tiny differences in density present shortly after the universe began were slowly amplified by gravity over billions of years. Regions that contained just slightly more matter gradually attracted more still. The process was astonishingly slow, yet relentless. Once again, gravity demonstrated its quiet persistence. Unlike a sculptor who removes stone with visible strokes, gravity shapes the universe almost invisibly. It asks for immense amounts of time, and in return, it creates galaxies, clusters, and structures so large that light itself requires millions of years to cross them. Perhaps patience is one of the universe's most creative forces. The same principle appears in places much closer to home. A river does not carve a canyon in a single season. A forest does not become ancient in one generation. Coral reefs slowly accumulate through countless tiny lives, building upon one another. Lasting structures often emerge through steady repetition rather than sudden change. Meanwhile, a faint glow fills all of space. It comes from every direction with remarkable uniformity, surrounding every galaxy, every planet, and every drifting cloud of gas. This gentle radiation is known as the cosmic microwave background. Although invisible to our eyes, it represents one of the oldest forms of light in existence. Nearly 13.8 billion years ago, the young universe was so hot and dense that light could not travel freely. Photons constantly scattered from charged particles, making the cosmos resemble a brilliant fog. As expansion continued, temperatures gradually fell. Eventually, atoms could form, allowing light to move across space without being endlessly interrupted. Those first freely traveling photons are still moving today. Over billions of years, the expansion of the universe has stretched their wavelengths, transforming what was once brilliant visible light into faint microwave radiation. Sensitive instruments aboard satellites have carefully measured this ancient glow, revealing subtle variations that preserve remarkable information about the early universe. In a sense, the oldest light has never stopped traveling. It has crossed expanding space for almost the entire history of the cosmos, quietly passing through galaxies that had not yet formed when its journey began. There is something deeply calming about imagining that ancient light continuing onward even now. As people sleep beneath quiet rooftops, as forests sway gently beneath moonlight, as waves meet distant shores, those ancient photons continue their patient voyage, indifferent to calendars or centuries. The universe rarely wastes motion. Even light keeps going. Elsewhere, some stars are so small that they spend their lives with extraordinary economy. Red dwarf stars, the most common type of star in our galaxy, shine far more gently than the sun. Their temperatures are lower, their light softer, and their fuel consumption remarkably efficient. Because they burn their hydrogen so slowly, many red dwarfs are expected to survive for trillions of years. This is a span of time far exceeding the current age of the universe. No red dwarf has ever reached the end of its full natural life. The universe is simply not old enough. This realization quietly reshapes our perspective. When we look toward these modest stars, we are observing objects whose greatest chapters still lie entirely in the future. They will continue shining through ages that no human civilization could ever witness. Long after brighter stars have completed their lives, countless red dwarfs may remain, patiently illuminating whatever planets still circle them. Sometimes endurance belongs not to the brightest, but to the gentlest. The largest stars live dramatically, but briefly. Their immense luminosity consumes fuel at extraordinary rates, allowing them to shine brilliantly for only millions of years before reaching spectacular conclusions. Red dwarfs choose another path. They burn slowly. They conserve. They persist. Nature offers many ways to exist. On Earth, similar patterns appear everywhere. A rushing stream may sparkle with energy, while a quiet underground aquifer patiently stores water for centuries. Wildflowers bloom brilliantly for a season, while old trees continue growing through generations. Neither way is better. Each follows its own rhythm. The universe seems comfortable, with many rhythms existing together. Meanwhile, planets continue orbiting stars throughout the Milky Way. Only a few decades ago, humanity knew of no confirmed planets beyond our solar system. Today, thousands have been discovered, and astronomers continue identifying more each year using increasingly sensitive techniques. Some reveal themselves by briefly dimming their stars as they pass across them. Others gently tug their parent stars back and forth through gravity, producing tiny motions detectable by careful instruments. Many are unlike anything found in our own solar system. There are worlds where glass may fall like rain. There are planets larger than Jupiter orbiting, astonishingly close to their stars. There are rocky planets slightly larger than Earth, and icy giants drifting through deep cold far from their suns. Scientists continue investigating which of these distant worlds might possess conditions suitable for liquid water, stable atmospheres, and perhaps even life. For now, many questions remain open, and there is peace in unanswered questions. They remind us that exploration is not a race toward completion. It is an ongoing conversation between observation and curiosity. Every new telescope extends that conversation a little farther. Every improved measurement adds another quiet sentence. Far above Earth's atmosphere, observatories orbit without the interference of weather or daylight. Their mirrors patiently gather faint light that has traveled across unimaginable distances. Some observe visible wavelengths. Others examine infrared radiation, X-rays, radio waves, or gamma rays, each revealing different aspects of the same universe. No single telescope sees everything. Together, they resemble many thoughtful listeners, each paying attention to a different voice within a vast cosmic choir. This diversity of observation has transformed our understanding of the heavens. Clouds of dust that appear dark in visible light glow warmly in infrared observations. Violent regions around black holes shine brightly in X-rays. Cold hydrogen gas quietly announces its presence through radio emissions. The universe has many languages. Science learns them gradually. Meanwhile, here on Earth, night settles over deserts where enormous telescopes rest beneath exceptionally clear skies. The air becomes still. Temperatures slowly fall. Domes quietly rotate toward carefully chosen targets. The observatory itself almost seems to breathe. Computers hum softly. Motors move with measured precision. Above, the stars continue their ancient patterns. Inside, astronomers collect photons that may have begun their journeys before human civilization existed. There is something beautiful about this meeting. Ancient light, modern curiosity, a quiet mountain, a patient instrument. Together, they create new understanding without disturbing the silence surrounding them. Elsewhere, beneath polar skies, ice preserves another kind of history. Layer upon layer of snowfall has accumulated over hundreds of thousands of years, each season leaving behind tiny traces of the atmosphere in which it formed. By drilling deep into glaciers and ice sheets, scientists recover long cylinders of ancient ice whose layers resemble pages within an unusually patient book. Tiny bubbles trapped inside contain samples of prehistoric air. They allow researchers to study Earth's changing climate across immense spans of time, revealing cycles of warming and cooling long before written history began. Even frozen water becomes an archive. Nature has many ways of remembering. Tree rings remember growing seasons. Sedimentary rocks remember ancient oceans. Fossils remember forgotten ecosystems. Starlight remembers distant ages. Ice remembers old skies. The universe seems quietly devoted to preserving its own story. And perhaps that is why astronomy feels so deeply connected to time itself. Every observation carries memory. Every distant object appears not only where it is, but also when it was. Every beam of light arriving tonight has crossed its own unique history before meeting your eyes. As the hours continue passing softly, and the imagined night around us grows deeper still, it becomes easier to appreciate that the universe has never hurried any of these journeys. Not the drifting of galaxies, not the birth of stars, not the slow orbit of quiet planets, not the ancient light crossing the darkness. Everything unfolds with remarkable patience. And in that patient unfolding, there is a gentle invitation to become still ourselves, if only for a little while, and simply accompany the universe as it continues its long, quiet voyage through time. There is another kind of light that quietly fills the universe, though it rarely captures our attention in the way a bright star or a nearby planet might. It is not concentrated into a single point, nor does it belong to one particular galaxy. Instead, it is spread across the heavens as an almost immeasurable glow, built from the combined radiance of countless stars that have lived throughout cosmic history. Astronomers sometimes speak of the extragalactic background light, a faint illumination created by generations of galaxies shining across billions of years. Every star that has quietly released its light into space has contributed, in some small way, to this subtle cosmic brightness. Most of those individual stars are far too distant to distinguish on their own. Yet together, they create a gentle record of the universe's long history of starlight. It is a comforting thought that even the faintest contributions become part of something larger. A single candle may illuminate only a small room, but thousands of distant lights can softly brighten an entire landscape. In much the same way, the accumulated glow of innumerable stars becomes another quiet thread woven through the fabric of the cosmos. Meanwhile, in the vast darkness between those stars, tiny grains of cosmic dust continue their slow journeys. Dust may sound ordinary, even insignificant, but in astronomy, it plays a remarkable role. These microscopic particles, made from elements such as carbon, silicon, oxygen, and iron, are often created in the gentle winds of aging stars or in the expanding remnants of stellar explosions. Carried outward into interstellar space, they drift for millions of years before becoming part of something new. Some grains eventually settle into molecular clouds where future stars are forming. Others become incorporated into young planets. Some may remain suspended between the stars for ages beyond imagination, quietly reflecting or absorbing passing light. The dust that gathers beneath a bookshelf over a single season reminds us that time is always leaving gentle traces. Cosmic dust performs a similar task across the universe, though on scales so vast that entire civilizations might come and go before a cloud noticeably changes its shape. Far beneath Earth's oceans, fine sediments settle through still water in much the same patient way. Each tiny particle drifts downward almost invisibly, eventually coming to rest upon the seafloor. Year after year, layer after layer accumulates until ancient climates, volcanic eruptions, and changing ecosystems become preserved within quiet bands of stone. Whether beneath an ocean or between the stars, small things often accomplish remarkable work simply by continuing. Elsewhere, some of the oldest stars in the Milky Way continue shining with extraordinary age. These ancient stars formed when the universe itself was still young. They contain very small amounts of elements heavier than hydrogen and helium, because relatively few earlier generations of stars had yet enriched the cosmos with newly forged materials. To astronomers, such stars resemble living historical documents. Their chemical composition quietly preserves information about an era when galaxies were only beginning to take shape. By carefully studying the light from these elderly stars, researchers can reconstruct parts of the Milky Way's earliest history, much as archaeologists learn about ancient civilizations through fragments of pottery or weathered foundations. The stars keep records in their own language. Their temperatures, motions, brightness, and chemical signatures each become gentle clues within a much larger story. Reading those clues requires remarkable patience. Modern observatories often collect light from a single faint object for many hours. Individual photons arrive one by one, each carrying only a tiny amount of information. Gradually, enough accumulate for a detailed spectrum to emerge, revealing the presence of different elements through delicate patterns of absorption and emission. Knowledge itself sometimes arrives photon by photon. There is something wonderfully appropriate about that. Many worthwhile understandings in life also emerge gradually. A friendship deepens through countless conversations rather than one remarkable afternoon. A forest becomes familiar after many quiet walks. A piece of music reveals new details each time it is heard. The universe rarely insists upon immediate understanding. Instead, it rewards gentle attention. Meanwhile, stars continue to age according to their mass. For stars much larger than our sun, the later stages of life become increasingly complex. After exhausting the hydrogen in their cores, they begin fusing heavier elements in successive layers, rather like the concentric skins of an onion. Helium becomes carbon. Carbon may become neon, oxygen, or magnesium. Still, heavier elements appear as temperatures continue rising. Each stage grows progressively shorter. What lasted millions of years eventually becomes thousands, then years, then perhaps only days for the final phases inside the most massive stars. Yet even here, the underlying processes remain governed by the same quiet physical laws that have operated since the universe began. There is no urgency in nature itself, only steady cause and effect unfolding exactly as conditions allow. Eventually, the core can no longer produce enough energy to support itself. Gravity, patient as always, resumes its inward work. The result may be a supernova, one of the brightest events in the universe. Although the explosion itself is extraordinarily energetic, it is worth remembering that it represents the conclusion of a story that has unfolded over millions of peaceful years. The brilliant finale occupies only a tiny fraction of the star's overall life. Even dramatic moments are often surrounded by vast expanses of quiet. From those stellar endings come many of the elements that later become planets, oceans, and living creatures. Gold, uranium, and many other heavy elements owe their existence to these rare events. Without them, Earth would be a profoundly different world. In this way, even endings quietly prepare possibilities for distant futures they will never witness. A star cannot know that its final gift will one day become part of mountains warmed by morning sunlight, or the iron carried through the blood of curious beings looking back toward the night sky. Yet the universe allows such remarkable continuities. Nothing is entirely isolated. Matter changes its arrangement. Energy changes its form. The story continues. Closer to our own time, the moon continues circling Earth with familiar steadiness. Its motion feels so dependable that it is easy to imagine it remaining unchanged forever. Yet even the moon participates in slow evolution. Each year, it drifts away from Earth by about 3.8 centimeters. The change is driven by tides. As Earth's oceans respond to the moon's gravity, tiny amounts of energy are transferred through the continual rise and fall of water. Over immense spans of time, this causes Earth's rotation to slow slightly while the moon gradually moves into a higher orbit. No one standing beneath tonight's sky could notice the difference. Even over many human lifetimes, the change remains essentially invisible. Yet over hundreds of millions of years, it becomes significant. Long ago, when dinosaurs wandered ancient landscapes, the moon was noticeably closer than it is today. The days themselves were slightly shorter. Time quietly reshapes even the motions we consider permanent. The stars remind us of this again and again. Constellations seem fixed because human lives are brief. Given enough time, however, every familiar pattern changes. The bright stars of Orion travel through space independently. The graceful curve of the Big Dipper slowly evolves. Future observers, living tens of thousands of years from now, would inherit skies that are recognizably connected to ours, yet gently transformed. The heavens are not frozen. They simply move with extraordinary patience. Imagine sitting beside a calm lake before dawn. The water appears perfectly still. Only after watching carefully for many minutes do you notice the almost invisible ripples spreading across its surface. The universe often asks for the same kind of attention. Its greatest motions reveal themselves only to those willing to compare ages rather than moments. Meanwhile, somewhere within a quiet molecular cloud, another generation of stars is already beginning to gather. Gravity slowly draws hydrogen inward. Temperatures rise. Tiny concentrations become denser. Perhaps planets will eventually form there. Perhaps one rocky world will develop oceans beneath gentle sunlight. Perhaps chemistry will discover new pathways toward life. Scientists continue investigating how frequently such conditions arise. The answer remains uncertain. Yet uncertainty itself leaves room for peaceful imagination. The cosmos is vast enough to hold possibilities beyond our present knowledge. Whatever those possibilities may be, they too will unfold gradually. Nothing in the universe seems eager to skip ahead. Everything arrives in its own season. As we continue this long journey toward the distant future of the cosmos, where stars themselves will eventually begin to disappear one by one, it is helpful to remember how much quiet abundance still surrounds us. The night sky of today belongs to one chapter among many. It is neither the beginning nor the end. It is simply one peaceful moment in a story written across almost unimaginable spans of time. A story that continues softly and patiently with every star that shines, every photon that travels through darkness, and every curious mind that pauses beneath the heavens long enough to notice. As we continue gently forward through the immense history of the cosmos, it is worth lingering for a little while in the present age of stars, because in many ways we happen to live during one of the universe's quieter and more luminous chapters. Astronomers sometimes describe our era as one in which starlight is abundant. Across hundreds of billions of galaxies, countless stars continue to burn their nuclear fuel, illuminating planets, warming clouds of gas, and quietly enriching space with the elements from which future generations of worlds may someday emerge. This age will not last forever, but there is no need to hurry toward its ending. On cosmic timescales, the universe still has an astonishing amount of gentle work ahead of it. Even now, new stars continue to form inside vast molecular clouds, where gravity patiently gathers cold hydrogen into slowly shrinking pockets. If one could observe such a cloud over several million years in only a few moments, it might resemble the gradual opening of flowers after a spring rain. Here and there, soft points of light would awaken within the darkness, each beginning its own extraordinarily long life. Most of these newborn stars will never know one another. They will drift apart as their galaxy slowly turns, each carrying its own family of planets, comets, asteroids, or perhaps nothing at all. The universe rarely builds identical worlds. Instead, it seems to enjoy quiet variety. Some stars shine with a cool reddish glow. Others burn white or pale yellow. A few, far larger and hotter, radiate a gentle blue light before spending their fuel relatively quickly. Yet despite these differences, every star is governed by the same simple balance between gravity and pressure. There is comfort in discovering unity beneath diversity. The same laws that guide the smallest red dwarf also govern the brightest giant. The same gravity that shapes galaxies gently keeps your feet upon the earth. Nature speaks many dialects, but it follows one remarkably consistent grammar. Meanwhile, around many stars, planets continue circling in silent obedience to gravity. Some complete an orbit in only a few days. Others require centuries. In our own solar system, Neptune takes about 165 Earth years to travel once around the Sun. A child born during the discovery of Neptune has never lived long enough to celebrate even a single Neptunian year. Time itself changes depending on where one chooses to measure it. A year is not an absolute quantity. It is simply one complete journey. Earth has its year. Mars has another. Jupiter measures time differently still. Far beyond them, small icy worlds trace such enormous orbits that one complete circuit around the Sun may require thousands of Earth years. Even within one solar system, clocks quietly disagree. Perhaps this reminds us that many things we consider permanent are simply local habits of nature. Meanwhile, sunlight continues spreading outward in every direction. Only a tiny fraction reaches Earth. Much of it travels into empty space, never warming a planet or reflecting from a moon. It simply continues. Some photons will cross the Milky Way. Others will leave our galaxy entirely. Many will continue traveling long after the Sun itself has ceased to exist. Light is wonderfully persistent. Unlike travelers who require rest, it never grows tired. Once released, it simply moves onward through expanding space until something eventually absorbs it, or perhaps for far longer than we can easily imagine. There is something peaceful in this endless journey. Every sunrise sends countless new messengers outward into the universe, carrying quiet evidence that our little star once shone here. Far away, perhaps no one will ever observe them. Yet they travel all the same. Nature does not seem concerned with being witnessed. Flowers bloom in valleys where no people walk. Snow falls across empty tundra beneath silent northern skies. Stars illuminate regions of space that no living eyes may ever see. Beauty appears to be entirely comfortable existing without an audience. Elsewhere, among the oldest star clusters, time has already performed much of its patient work. Globular clusters are remarkable gatherings containing hundreds of thousands, and sometimes millions, of stars bound together by gravity. Many formed during the earliest chapters of galactic history and have remained together for more than 12 billion years. If one could somehow stand upon a planet inside such a cluster, the night sky would be astonishing. Instead of scattered stars separated by wide expanses of darkness, thousands of brilliant suns might crowd the heavens. Night would never become truly dark. The sky itself would seem almost woven from starlight. Yet even there, despite such overwhelming beauty, silence would remain. Sound cannot cross the emptiness between stars. The universe's brightest landscapes are still profoundly quiet. Perhaps silence is not the absence of activity. Perhaps it is simply the natural companion of great distance. The stars perform extraordinary work every second. Galaxies rotate, planets orbit, comets wander. Black holes slowly influence everything around them, and yet almost all of it unfolds without a single sound. Our imaginations often fill space with music because true silence is difficult to picture. But the real universe is gentler than many stories imagine. It is a place where motion usually occurs without noise, where light travels alone, where gravity speaks without words. Meanwhile, on Earth, entirely different rhythms continue beneath familiar skies. Deep within old forests, fungi slowly connect the roots of neighboring trees through delicate underground networks. Nutrients pass quietly from one organism to another. Ancient trees may gently support younger saplings growing in deep shade. The forest appears still from above. Yet, beneath fallen leaves, an intricate conversation quietly continues. Nature often hides its greatest activity beneath calm surfaces. The same is true beneath the ocean, far below the reach of sunlight, where darkness has remained unbroken for millions of years. Strange communities thrive around hydrothermal vents. Here, superheated water rich with dissolved minerals rises from cracks in the seafloor. Instead of relying on sunlight, many organisms obtain energy through chemical reactions involving sulfur compounds. Life has discovered another path. These deep ecosystems remind us that sunlight, although precious to us, is not the only source of possibility. Scientists continue studying such environments because they may offer clues about how life first appeared on Earth, and perhaps how it might survive elsewhere. One possibility is that similar conditions could exist beneath the icy shells of distant moons. Europa, orbiting Jupiter, almost certainly hides a vast ocean beneath its frozen surface. Enceladus, one of Saturn's smaller moons, sends graceful plumes of water vapor and ice into space through fractures in its icy crust. These worlds receive very little sunlight, yet beneath their frozen exteriors, liquid water may persist, warmed not by the sun, but by the continual flexing of their interiors under gravity. Whether life exists there remains unknown. Current evidence does not yet provide an answer. Still, these quiet oceans invite careful curiosity rather than hurried conclusions. Perhaps somewhere beneath kilometers of ancient ice, water has remained peacefully circulating for millions of years, untouched by wind or weather, illuminated only by the faint warmth rising from the moon's rocky heart. If so, those hidden seas have been waiting with extraordinary patience. The universe seems filled with places that reward patient observation, not because they conceal secrets intentionally, but because their stories unfold slowly enough that understanding requires time. Meanwhile, our own sun continues its gentle journey around the center of the Milky Way. One complete orbit takes roughly 230 million Earth years. Since the dinosaurs disappeared, the solar system has traveled only partway through another circuit. Human civilization occupies an almost unimaginably tiny fraction of that single galactic year. And yet, within that brief interval, people have learned to measure the motions of planets, detect galaxies billions of light years away, and reconstruct much of the universe's history. knowledge itself has expanded remarkably quickly. Still, compared to the cosmos, it remains wonderfully humble. Every answer reveals new questions. Every telescope uncovers fainter horizons. Every generation inherits mysteries alongside understanding. Perhaps that is exactly as it should be. A universe capable of being fully exhausted by curiosity would somehow feel smaller. Instead, the horizon continues gently retreating as our understanding quietly grows. There is no finish line waiting beyond the next discovery. Only another peaceful landscape inviting careful attention. And somewhere, far beyond the most distant galaxies visible today, space continues expanding just as it has for billions of years, carrying every great cluster, every quiet star, and every wandering photon a little farther into the immeasurable darkness, where the long future of the universe waits with the same patient silence that has accompanied it since the very beginning. As the universe continues its slow expansion, another subtle transformation is quietly unfolding, one so gradual that it cannot be noticed over a single lifetime, or even across the entire span of recorded human history. The galaxies themselves are not only changing from within as stars are born and age, they are also becoming more isolated from one another, carried gently apart by the stretching of space. For much of cosmic history, gravity and expansion have shared an intricate conversation. Gravity gathers matter together, encouraging stars, galaxies, and clusters to form. Expansion gently increases the distance between structures that are not bound together. Neither force is hurried. Both shape the universe with extraordinary patience. Today, observations suggest that the expansion of the universe is accelerating. Scientists attribute this behavior to something we call dark energy, though the name describes our observations more than it explains the underlying cause. Current evidence indicates that dark energy makes up most of the total energy content of the universe, yet its true nature remains one of the deepest open questions in modern cosmology. There is something quietly humbling about this. After centuries of careful observation and remarkable scientific progress, we find that much of the cosmos is still only partially understood. The unknown has not disappeared as knowledge has grown. In many ways, it has become more clearly defined. Rather than shrinking, the horizon of mystery has simply moved farther away. Imagine standing on the shore of a calm sea at dawn. As the first light spreads across the water, more of the coastline becomes visible. Yet beyond that newly illuminated horizon still lies another, waiting patiently beyond sight. Science often progresses in much the same way. Every answer gently reveals another question resting just beyond it. Meanwhile, galaxies continue their graceful rotations. Within the Milky Way, our sun quietly follows its familiar orbit, passing through regions that differ only subtly over millions of years. Spiral arms are not rigid structures, but rather long-lived patterns, somewhat like gentle traffic flowing through a city. Stars move into these regions, spend time within them, and gradually move onward again. The spiral itself endures. The individual stars slowly change places. Patterns, it seems, often outlive the individual pieces from which they are made. One might think of waves moving across the surface of a quiet lake. The water itself is constantly changing position. Yet, the graceful shape of the wave appears to persist. Nature frequently builds lasting forms from continually changing parts. Our own bodies quietly demonstrate the same principle. Over many years, countless cells are replaced. The air we breathe becomes part of us before returning to the atmosphere. Water passes through rivers, clouds, oceans, and living creatures in one continuous cycle. Permanence is often more gentle than absolute. It exists as continuity rather than stillness. Elsewhere among the stars, white dwarfs continue their remarkably slow cooling. When stars like our sun complete their red giant phase, they leave behind dense stellar remnants no larger than Earth, but containing roughly half the sun's original mass. These white dwarfs possess no ongoing fusion. They shine simply because they remain warm. Very warm. At first, their temperatures can exceed 100,000 degrees. Yet, without new energy being generated, they begin an extraordinarily long process of cooling. Not over centuries, not over millions of years, but over trillions upon trillions of years. The universe has not yet existed long enough for even a single white dwarf to cool completely. Every white dwarf ever formed is still slowly releasing the heat stored within it. Astronomers sometimes imagine the distant future when these objects eventually become black dwarfs, cold, dark stellar remnants that emit almost no visible light. But this remains a theoretical future. The universe is still far too young. No black dwarfs exist yet. This is one of those delightful reminders that some chapters of cosmic history still belong entirely to the future. The universe has not finished writing its own story. Far from it. Many of its longest chapters have not yet begun. Meanwhile, neutron stars continue spinning through the darkness. These extraordinary objects are created when massive stars end their lives and their cores collapse under gravity. A neutron star may contain more mass than our sun compressed into a sphere only about 20 kilometers across. The density is almost beyond imagination. A single teaspoon of neutron star matter would weigh billions of tons under Earth's gravity. Yet, despite these astonishing numbers, neutron stars often spend their lives quietly rotating. Some complete hundreds of rotations every second. Others rotate more slowly, gradually losing energy over millions of years. Certain neutron stars produce beams of radio waves that sweep across space like the slow turning of a lighthouse. When one of these beams briefly crosses Earth, astronomers observe a pulse. The object itself does not blink. It simply rotates. Its steady rhythm creates the appearance of flashing. Nature often surprises us in this way. What first appears mysterious gradually becomes beautifully understandable. The explanation rarely removes the wonder. Instead, it changes its shape. Understanding how a rainbow forms does not make it less beautiful. Knowing why stars shine rarely diminishes the night sky. If anything, familiarity often deepens appreciation. The universe becomes more intimate as it becomes more understandable. Meanwhile, time continues flowing across Earth in ways both ordinary and profound. Morning light touches mountain peaks before reaching valleys. Fog slowly lifts from quiet rivers. Deserts release the warmth gathered during the day into cool evening air. Snow accumulates grain by grain upon silent forests. These familiar rhythms connect our lives to much larger cycles. Earth turns, the moon orbits, the planets continue their paths. The solar system circles the galaxy. The galaxy drifts among countless others. Layer upon layer of motion quietly unfolds beneath every ordinary day. When we watch the stars from a peaceful place on a clear evening, we often feel as though we are standing still. In truth, we are traveling at remarkable speed. Earth rotates at hundreds of meters each second. It orbits the sun at about 30 kilometers each second. The sun circles the Milky Way even faster. The Milky Way itself moves relative to neighboring galaxies. And yet none of this motion is felt. Movement without disturbance is one of nature's quiet gifts. Passengers aboard a smoothly moving ship often forget they are traveling. Likewise, our planet carries us gently through space with remarkable steadiness. There is comfort in that invisible journey. No engine roars. No vibration announces our passage. The universe simply continues carrying us onward. Elsewhere, tiny planets continue forming around young stars. Inside dusty disks, microscopic grains gently collide. Most encounters accomplish little. Some particles separate again. Others remain together. Little by little, larger structures emerge. Pebbles become boulders. Boulders become mountain-sized bodies. Eventually, gravity begins helping. What starts almost invisibly slowly becomes a world. The process resembles snowflakes gathering across an open field during a long winter night. One flake changes almost nothing. Millions quietly transform the landscape. The universe often builds greatness from repeated small beginnings. There is wisdom in that rhythm. We sometimes imagine important events arriving suddenly, fully formed. Yet mountains rise grain by grain. Languages evolve word by word. Forests spread seed by seed. Galaxies assemble star by star. Perhaps patience is not merely the passing of time. Perhaps it is the very method by which complexity comes into being. Far ahead, beyond spans of time, so enormous they scarcely fit within ordinary imagination, the pace of star formation will continue to decline. Galaxies cannot create new stars forever. The great clouds of cold hydrogen from which stars are born are gradually consumed or dispersed. Each new generation of stars leaves a little less raw material available for the next. The change is slow beyond comprehension. Even after billions more years, stars will still exist. Yet the universe's youthful abundance will gradually soften. Bright stellar nurseries that are common today will become less frequent. The cosmos will slowly grow quieter, not suddenly, not dramatically, simply through the patient use of what it already possesses. Like an old forest where young saplings still appear, but less often than in centuries past, the universe will continue renewing itself at an ever gentler pace. And throughout those immense ages, the darkness between the stars will become just a little wider, the galaxies just a little farther apart, while the remaining lights continue shining with the same quiet devotion that has always defined them, asking for nothing, announcing nothing, simply offering their steady glow to an expanding and wonderfully patient universe. With each passing billion years, the character of the universe changes almost imperceptibly. If one could somehow observe its history, as though watching the slow movement of clouds across an afternoon sky, entire eras would seem to drift into one another without clear boundaries. There is no single morning when the universe wakes to discover that it has become older. It simply continues, carrying every galaxy, every star, and every quiet world a little farther along its endless path. For a very long time to come, many familiar sights will remain. Galaxies will still contain rivers of stars. Planets will continue tracing patient circles around their suns. Comets will occasionally emerge from distant reservoirs of ice before retreating once more into the darkness. Across countless systems, dawn and evening will continue to alternate wherever worlds still turn beneath their skies. Yet beneath this reassuring continuity, small changes slowly accumulate. Astronomers sometimes compare the universe to an enormous garden that has entered late summer. Flowers still bloom, birds still cross the sky, trees remain full of leaves. Nothing feels empty, yet the seasons are quietly advancing, and the earliest hints of autumn already exist within the changing light. The universe, too, is gradually moving toward a quieter season. The great stellar nurseries that once filled young galaxies with brilliant blue stars become less active over time. The brightest, most massive stars have always lived brief lives. They shine generously, consume their fuel quickly, and quietly pass their material back into space. What remain increasingly are the slower stars, the patient ones, the red dwarfs, the long-lived white dwarfs, the quiet companions that seem content to shine gently for unimaginable stretches of time. It is almost as though the universe itself gradually adopts a calmer pace. Its youth was filled with frequent creation. Its maturity becomes defined by endurance. Meanwhile, within galaxies, gravity continues arranging stars into ever-changing patterns. Individual encounters between stars remain extraordinarily rare because space is so spacious. Even in regions where stars appear densely packed, the distances separating them are difficult to imagine. If our sun were reduced to the size of a small marble, the nearest neighboring star would still be several hundred kilometers away. The emptiness between stars is not a small gap. It is the rule. The stars themselves are exceptions. This perspective gently reshapes the night sky. When we look upward, our eyes naturally notice the points of light. Yet almost everything we are looking at is the quiet darkness between them. The universe is composed not only of luminous objects, but also of immense expanses where almost nothing interrupts the silence. And somehow, that vast emptiness does not diminish the beauty of the stars. It gives them room to breathe. A single lantern shines most softly when surrounded by darkness. Likewise, the night sky owes much of its peaceful character to the generous spaces separating its lights. Elsewhere, planets continue evolving according to their own quiet histories. Some lose their atmospheres as their stars gradually brighten. Others remain frozen beneath thick shells of ice for billions of years. Gas giants slowly cool after retaining the warmth left over from their formation. Rocky worlds experience mountain building, volcanic eruptions, erosion, and long cycles of climate, each unfolding according to local conditions. No two planets tell exactly the same story, yet each follows the same patient laws of physics. Gravity shapes mountains. Heat moves through stone. Atmospheres circulate. Water, where it exists, quietly reshapes the land, one drop at a time. The language changes. The grammar remains familiar. Closer to home, Earth itself continues changing with remarkable steadiness. The continents drift only a few centimeters each year, about as quickly as fingernails grow. It is a movement so gentle that no one notices it from one season to the next. Yet over hundreds of millions of years, oceans open and close. Mountain ranges rise. Ancient coastlines disappear beneath new seas. Places that were once tropical become covered in snow. Regions now buried beneath oceans may someday become dry land again. The surface of our world is never truly finished. It is quietly rewriting itself. Geologists often think in these immense intervals, almost as naturally as historians think in centuries. A rock can preserve memories that no written record could ever contain. Layers of sandstone remember ancient deserts. Limestone recalls warm, shallow seas filled with tiny marine organisms. Basalt speaks of flowing lava that cooled long before mammals appeared. Even the earth beneath our feet has learned patience from deep time. Meanwhile, the sun itself slowly changes in ways almost impossible to notice directly. Every billion years or so, its brightness increases by roughly 10%. This gradual change influences every planet that orbits it. Over immense spans of time, the habitable region around the sun slowly shifts outward. Worlds that were once comfortably warm may become too hot. Frozen regions farther away may briefly experience conditions that allow liquid water. Nothing remains fixed forever, not because the universe is unstable, rather because it is alive with continual, gentle change. Even stability has its own quiet evolution. Far beyond the solar system, enormous clouds of interstellar gas continue drifting through galaxies. Some are illuminated by nearby stars, glowing softly in shades of red, blue, and violet. Others remain almost completely dark, their dust so dense that visible light cannot easily pass through. Within these shadowed regions, gravity quietly begins new work. Future stars already exist there as possibilities. The cloud does not know which parts will someday ignite. It simply continues drifting. Small fluctuations slowly grow. Tiny differences become meaningful over millions of years. There is a lesson hidden within such clouds. Great outcomes often begin as almost invisible variations. A slight increase in density, a small imbalance, a gentle pull sustained for a very long time. Nature often accomplishes extraordinary things without dramatic beginnings. Meanwhile, throughout the observable universe, light continues arriving from increasingly distant places. Some of that light left its source before Earth possessed complex life. Some departed before our sun had formed. Some has traveled for nearly the entire age of the universe. Every night sky, therefore, contains many different ages layered together. Nearby stars belong to a relatively recent past. Distant galaxies reveal far older chapters. The cosmic microwave background reaches us from an age when no stars yet existed. Looking outward becomes an act of quiet time travel. The farther we see, the younger the universe appears. Yet the observer remains here, in the present, gently collecting messages sent across unimaginable spans of time. There is something deeply reassuring about this conversation across ages. The universe has never stopped telling its story. It simply speaks very slowly. A photon leaving a distant galaxy begins a journey without knowing whether anyone will ever receive it. Billions of years later, it may gently strike the mirror of a telescope resting atop a mountain beneath clear night skies. From that single tiny arrival, astronomers may infer the existence of entire galaxies, estimate their ages, measure their motions, and learn something new about the history of the cosmos. An immense story can travel inside a single particle of light. The universe seems remarkably economical in that way. Elsewhere, old star clusters gradually become even older. The brightest members quietly disappear first, leaving behind populations increasingly dominated by smaller, longer-lived stars. Over time, the overall color of these ancient clusters slowly shifts toward warmer shades. Astronomers can estimate the age of a cluster simply by observing which kinds of stars remain. The stars themselves become clocks, not clocks with hands or numbers. Clocks whose passing time is written in color, brightness, and temperature. Nature often measures time through transformation rather than counting. A seed becomes a tree. Snow becomes water. Stone becomes sand. Hydrogen becomes helium. Each change quietly marks the passage of another chapter. And perhaps this is why the future of the universe feels less like an ending than a long continuation. There is no sudden page where the story simply stops. Instead, the cosmos gradually softens. Its brightest lights become less common. Its galaxies become more isolated. Its rhythms become slower still. The great symphony does not end with a final crashing note. It becomes quieter movement by movement, allowing each remaining star to shine a little longer in the vast, gentle darkness. that has always surrounded them. As the long ages continue to unfold, there comes a time when the night skies of many future worlds begin to look different from the skies we know today. The change is not sudden. No observer would wake one morning to find the heavens transformed. Instead, generation after generation would inherit a sky almost identical to that of their ancestors, while over billions upon billions of years, the accumulated differences would quietly become profound. Our own local group of galaxies, bound together by gravity, will remain a close family for an extraordinarily long time. The Milky Way and Andromeda, after their slow encounter and eventual merging, will gradually settle into a single, larger galaxy. Smaller companion galaxies will also become part of this immense stellar home, each contributing its stars to the growing collection. From within that future galaxy, the night sky may be breathtaking. There could be dense rivers of ancient stars stretching from horizon to horizon. Bright globular clusters might drift like softly glowing lanterns through the darkness. The familiar constellations known to us today will have long since dissolved, replaced by entirely new patterns that no human has ever imagined. And yet, despite this richness nearby, something subtle will be missing. The distant galaxies beyond the local group will have continued drifting away as the universe expands. Little by little, their light will become more difficult to detect. Eventually, many of them will recede beyond what astronomers call the cosmic event horizon. Their light, emitted after a certain point, will never reach observers within our future galaxy, because the expansion of space carries those distant regions away faster than the light can bridge the growing distance. It is an unusual idea. Nothing dramatic happens to those galaxies themselves. They continue evolving. Stars continue shining within them. Planets continue orbiting. Their own quiet histories unfold as always. They simply become unreachable. The universe gently places more space between distant neighbors until conversation through light is no longer possible. There is a certain melancholy in this image, but it is not a lonely one. After all, every galaxy continues existing within its own peaceful surroundings. Nothing is destroyed by this increasing separation. Rather, each island of stars slowly becomes more self-contained, carrying its own history through the expanding cosmos. If future astronomers living trillions of years from now were to study the heavens, their understanding of the universe might differ greatly from ours. Without visible distant galaxies, they could reasonably conclude that their galaxy represented almost the entire observable universe. The evidence we possess today would have quietly slipped beyond their horizon. Science, like every human endeavor, depends upon what nature allows us to observe. We happen to live during a fortunate era. The expansion of the universe has progressed far enough for us to measure it, yet not so far that most galaxies have disappeared from view. In this sense, our place in cosmic history offers a particularly broad window. Windows, however, are meant for looking through rather than holding on to. Every age receives its own view. future observers will have different questions, different evidence, different mysteries. The universe never stops inviting curiosity. Meanwhile, inside the merged galaxy, the remaining stars continue following their long, graceful orbits. Unlike the elegant spiral structure of today's Milky Way, the new galaxy may resemble a giant elliptical system, with stars moving along a wide variety of paths rather than neatly organized spiral arms. The galaxy becomes calmer. The great blue star-forming regions that once decorated spiral arms become increasingly uncommon. Much of the available cold gas has already been transformed into stars or gently dispersed. The galaxy begins to resemble an old forest, not empty, not lifeless, simply mature. Ancient trees stand quietly beneath broad canopies. Young saplings still appear from time to time, but less frequently than before. The forest possesses a different kind of beauty than it did in its youth. The universe seems to appreciate every season. Some galaxies remain active for longer than others. Occasional mergers still bring fresh material. Small clouds of gas continue collapsing into new stars. Yet overall, the pace becomes slower. Creation continues, but with increasing gentleness. Astronomers refer to this broad decline as the gradual reduction in the cosmic star formation rate. The universe is not running out of stars. Rather, it is becoming more selective in creating new ones. The brightest years of stellar birth slowly fade into memory. Still, countless stars remain. Red dwarfs, especially, continue their patient existence. Their modest brightness, once overshadowed by larger neighbors, becomes increasingly important. These quiet little stars inherit much of the future. They continue converting hydrogen into helium with remarkable efficiency. Some may shine for 10 trillion years, others perhaps much longer. No human experience offers an intuitive comparison for such durations. If the entire current age of the universe were compressed into one day, the future lives of many red dwarfs would continue for months beyond that single day. Their patience almost defies imagination. Perhaps there is something reassuring about the smallest stars becoming the longest lived. The universe does not always reward brilliance with longevity. Sometimes gentleness proves remarkably enduring. Meanwhile, the white dwarfs born from countless earlier generations of stars continue cooling. At first, they remain faintly luminous, glowing with stored thermal energy. As trillions of years pass, they become progressively dimmer. The process is so slow that language begins to struggle. There are few everyday experiences that prepare us for events unfolding across trillions of years. Even mountains seem fleeting by comparison. Entire galaxies evolve, while a white dwarf quietly loses a little more warmth. Scientists calculate these cooling rates through careful models of stellar physics, though the full journey extends far beyond any observational record. Nature has already written the equations. Time has simply not yet completed the experiment. Elsewhere, neutron stars drift silently through the galaxy. Some remain members of binary systems, orbiting quiet companions. Others travel alone after receiving gentle gravitational kicks during the supernovae that created them. Their powerful magnetic fields gradually weaken. Their rapid rotations slowly decrease. One more patient process, one more quiet transition. Across the galaxy, black holes also continue their long existence. Most formed from massive stars that completed their lives billions or trillions of years earlier. Others occupy the centers of galaxies, containing millions or billions of times the mass of our sun. Despite their reputation for endless appetite, many spend vast stretches of time remarkably inactive. If little material falls toward them, they simply wait. Gravity itself never becomes impatient. There is an interesting symmetry here. The universe often pairs extraordinary power with extraordinary restraint. A supermassive black hole capable of shaping an entire galaxy may spend millions of years doing almost nothing noticeable. A red dwarf capable of shining for trillions of years does so with quiet modesty. Even the largest structures often behave gently. Meanwhile, planets continue circling stars that have not yet reached the ends of their lives. Some of those worlds may still possess oceans. Some may host atmospheres beneath unfamiliar constellations. Some may remain frozen beneath endless ice. If life exists elsewhere in the cosmos, many distant civilizations, if they arise at all, would experience these far future skies as entirely normal. To them, ancient spiral galaxies visible in our own age might seem like forgotten legends, much as dinosaurs seem ancient to us. Every generation considers its own sky ordinary. Yet, every sky belongs to a unique chapter of cosmic history. Back on Earth, if we briefly return in imagination to our own time, the familiar rhythm of evening continues. Clouds drift across moonlight. Owls move quietly through forests. Tides rise and fall beneath patient stars. The same universe that governs the future cooling of white dwarfs also guides the gentle movement of waves along a quiet shoreline tonight. There is no separation between the immense and the intimate. The laws shaping galaxies also shape raindrops. The atoms forged inside ancient stars now rest within leaves, rivers, mountains, and living beings. The story has always been continuous. Perhaps this continuity offers its own quiet comfort. The future of the universe is not an entirely different tale. It is simply the present, carried forward with extraordinary patience. Every second becomes a minute. Every year becomes a century. Every billion years becomes another chapter. Nothing hurries. Nothing skips ahead. The cosmos simply continues, allowing each star, each galaxy, and each beam of light to complete its own long journey, one gentle moment at a time, beneath a silence that has accompanied the universe since its earliest dawn, and will remain with it through ages, still waiting patiently to arrive. As the trillions of years continue to pass, the universe gradually enters an era unlike any that has come before. It is not marked by catastrophe, nor by a sudden extinguishing of the stars. Instead, It is characterized by an almost imperceptible slowing of creation. The great furnaces of stellar birth, once common throughout countless galaxies, become increasingly uncommon. There are still stars, there is still light, there is still warmth, but the balance has shifted. For much of cosmic history, new stars were born more quickly than old ones disappeared. Galaxies were lively places, filled with glowing nebulae, where fresh generations quietly emerged from cold clouds of hydrogen. Eventually, however, those immense reservoirs begin to grow thin. Every star carries away a small portion of the available hydrogen, transforming it into heavier elements through the steady work of nuclear fusion. Although some material is returned to space when stars reach the ends of their lives, not all of it finds its way back into the cold, dense clouds required for new stellar nurseries. The universe is remarkably generous with time. It is somewhat more careful with raw materials. This gradual change does not feel like scarcity. It feels more like the gentle settling of a landscape after a long season of growth. Imagine an ancient woodland where towering trees have stood for centuries. New saplings still appear in quiet clearings, but the frantic flourishing of youth has softened into a slower rhythm. Birds continue to sing. Wind still moves through the branches. The forest remains full of life, yet it carries the calm confidence of great age. The galaxies begin to resemble such forests. Their brightest chapters are behind them, but their beauty has become deeper rather than diminished. Meanwhile, the smallest stars continue shining almost without concern for these larger changes. Red dwarfs have always lived patiently. Now, their patience begins to define the age itself. These cool, modest stars consume their hydrogen so slowly that they scarcely seem to notice the passing of trillions of years. Their steady crimson light becomes one of the most familiar forms of illumination remaining in the cosmos. Around some of them, planets may continue their endless orbits. Days and nights may still alternate. If life has found a home on any of those distant worlds, their skies would be dominated by a warm reddish glow instead of the golden light we know from the sun. Sunsets, if atmospheres permit them, might linger in shades of deep amber and soft copper. Shadows would stretch gently across quiet landscapes. The stars visible at night would likely be fewer than those above Earth today, yet each would possess its own calm presence. There's something comforting about imagining that even so far into the future, somewhere, a horizon might still brighten with morning. Elsewhere, white dwarfs continue cooling with extraordinary patience. At first, they remain warm enough to emit visible light. As the ages accumulate, they glow first orange, then red, then faintly infrared, slowly slipping beyond what human eyes could perceive. Nothing forces this transition. It simply unfolds. The stored warmth that once illuminated these stellar remnants gradually radiates into the vastness of space. Each passing trillion years carries away another small measure of heat. If one could return to the same white dwarf again and again across these immense intervals, the changes would appear almost impossible to notice from one visit to the next. Yet, eventually, they would become undeniable. Nature often works through accumulation. One snowflake rarely changes a landscape. Millions transform an entire valley. One gentle wave scarcely alters a shoreline. Countless tides reshape continents. The cooling of white dwarfs follows this familiar pattern. Tiny changes become immense only because time continues faithfully onward. Meanwhile, in the quiet depths of space, gravity remains at work. Although new stars become increasingly uncommon, existing stellar remnants continue interacting over immense spans of time. Inside ancient star clusters, countless close encounters slowly alter the orbits of individual stars. The process is subtle. One passing star changes another's path only slightly. A million such encounters gradually reshape the entire cluster. Some stars gain enough speed to escape altogether, drifting into interstellar space. Others move closer toward the dense center. Over unimaginably long periods, entire star clusters slowly dissolve, not through violence, through patience. The stars simply wander away. If viewed in accelerated time, the cluster might resemble a handful of glowing embers gently dispersing into a calm night breeze. Eventually, only a few isolated companions remain before they too continue outward into the darkness. Even structures held together by gravity are not entirely permanent. Given sufficient time, quiet motion accomplishes remarkable things. The same principle applies on Earth. A cliff overlooking the sea may appear immovable, yet rain enters tiny cracks. Winter ice gently expands them. Wind carries away loose grains. Century after century, the cliff slowly changes its shape. No single storm performs the entire task. Time does. The universe repeatedly demonstrates that persistence often surpasses force. Meanwhile, galaxies themselves continue evolving. Within them, stars gradually spread into broader distributions. Some stellar remnants settle into stable orbits, lasting for unimaginable durations. Others are gently scattered by gravitational encounters. The overall appearance of these galaxies becomes smoother, calmer, and older. Bright blue stars, once symbols of vigorous youth, become exceedingly rare. The soft glow of ancient stellar populations comes to dominate. If colors could carry emotions, this future universe might feel painted in warm embers rather than brilliant flames. Scientists sometimes describe these distant eras collectively as the degenerate era. The name refers not to decline in an everyday sense, but to the kinds of objects that become most common: white dwarfs, neutron stars, black holes, brown dwarfs. These stellar remnants quietly inherit the cosmos after ordinary star formation has largely come to an end. It is a peaceful succession. The youngest generation gradually gives way to the elders. Nothing is hurried. Nothing is taken away abruptly. The universe simply grows older. Brown dwarfs also deserve a quiet moment of attention. These objects occupy an interesting place between stars and planets. They contain too little mass to sustain the long-term hydrogen fusion that defines ordinary stars, yet they are far more massive than giant planets. Some briefly fuse small amounts of deuterium early in their lives. Afterward, they spend countless ages slowly cooling. Astronomers sometimes call them failed stars, though that phrase can sound unfair. Brown dwarfs have not failed. They simply followed a different path. Nature rarely insists upon a single definition of success. A towering oak and a field of wildflowers each fulfill different roles. Likewise, brown dwarfs quietly contribute to the richness of the universe simply by existing as they are. Far into the future, these dim objects remain scattered throughout galaxies, glowing faintly with the residual warmth of their formation. Some wander alone through interstellar darkness. Others orbit ordinary stars. Still others travel with companions of their own. Each continues its patient cooling, joining the long procession of objects, slowly releasing their remaining heat. Heat itself has become one of the central characters in this distant chapter. Every warm object gradually shares its energy with the colder universe around it. This tendency is one of the most fundamental patterns in physics. A cup of tea cools upon a quiet table. Fresh lava hardens into black volcanic stone. A newly formed planet slowly releases the warmth left over from its birth. Stars shine because energy moves outward from their hot interiors. Again and again, nature gently smooths differences in temperature. The universe does not rush this process. It allows warmth to spread gradually, patiently seeking balance. This slow evening out of energy lies at the heart of the immense future we are approaching. Not because it is dramatic, quite the opposite. Its quiet persistence makes it unavoidable. For now, however, the cosmos still possesses countless reservoirs of stored energy. Ancient stars continue shining. White dwarfs continue glowing. Planets retain internal warmth. Black holes influence their surroundings through gravity. The story is far from over. The lights have merely become softer. And perhaps there is something deeply reassuring about that. The universe does not leap from brilliance into darkness. It lingers. It allows every remaining source of light to complete its own long farewell, each according to its nature, each following the same patient laws that have guided the cosmos from its earliest moments. As the ages drift onward like slow clouds across an endless night, the remaining stars continue their gentle vigil, illuminating an ever quieter universe, whose greatest gift has always been time itself, offered generously, without haste, to every atom, every world, and every distant point of light. As the universe continues its long and gentle progression into deep time, even the idea of stars begins to feel different, not because they vanish suddenly, but because their role in shaping the cosmos slowly diminishes. The era of active star formation fades, and what remains is a sky increasingly dominated by objects that no longer create new light, but instead preserve the memory of earlier brilliance. White dwarfs, neutron stars, black holes, and brown dwarfs become the quiet population of the cosmos. Each one carries a history written into its very structure. Each one is the result of earlier generations of stars that once lived, burned, and returned their material to space. In this way, even the darkest future objects are not endings in a true sense. They are transformations. The universe rarely discards anything entirely. It reshapes. White dwarfs, for instance, begin their long cooling journey surrounded by the faint glow of their past. At first, they still radiate visible light, but gradually, their emission shifts into infrared wavelengths. To human eyes, they would grow dimmer across unimaginable spans of time until they become almost invisible against the cold background of space. Yet, even then, they are not truly gone. They remain present in temperature, in gravity, in subtle influence over nearby objects. They simply stop announcing themselves in light. There is something almost meditative in this fading. It is not an abrupt disappearance, but a soft withdrawal, like embers slowly losing their glow beneath ash. Meanwhile, neutron stars continue their quiet existence in a different way. Some remain isolated, drifting through the galaxy like dense, silent relics. Others exist in binary systems, slowly exchanging matter with a companion star in a delicate gravitational balance that can last for billions of years. Their magnetic fields, once unimaginably strong, gradually weaken. Their rapid rotations slow, but only slightly over vast periods. Even the most extreme objects in the universe are subject to time's gentle influence. Nothing escapes it, not even the most tightly bound matter in existence. And yet, neutron stars also remind us that stability itself can take extraordinary forms. A single neutron star can remain structurally intact for longer than the current age of the universe by many orders of magnitude. It is a kind of endurance that has no direct counterpart in everyday experience. In comparison, even mountains are temporary. Black holes, too, continue their long and patient lives. Many of them, formed from the collapse of massive stars, drift silently through galaxies, rarely interacting with anything at all. Others sit at galactic centers, influencing the orbits of millions or billions of stars through gravity alone. Despite their reputation, most black holes are not active destroyers. They are simply gravitational objects waiting for matter to come close enough to be affected by them. And even then, their activity is intermittent. Long periods of stillness are punctuated by rare moments when gas, dust, or even a passing star falls inward and briefly lights up the region around them in a radiant disk of energy. Between those events, they remain quiet, still, unseen, almost absent except through their gravitational presence. In the far future, black holes become especially significant because they are among the longest-lived structures in the universe. While stars fade and galaxies disperse, black holes persist, slowly growing or remaining stable depending on their environment. And even they are not eternal. Over timescales, so vast they stretch beyond ordinary comprehension, they begin a subtle process of evaporation through what physicists describe as Hawking radiation. This phenomenon suggests that black holes can very gradually lose energy, emitting extremely faint radiation as quantum effects near their event horizons allow particles to escape. This process is so slow that, for all current astronomical objects, it is effectively negligible. But in the deep future, when nothing else remains bright, even this faint emission becomes meaningful. A black hole that once contained the mass of a star might take inconceivably long periods of time to fade away completely. Not years, not billions of years, but durations so large that even galaxies seem brief by comparison. This is not an ending that arrives suddenly. It is another form of slow transformation, consistent with everything else the universe does. Elsewhere, as black holes persist and white dwarfs cool, galaxies themselves begin to lose their familiar structure. Without fresh star formation to illuminate spiral arms, the graceful patterns that once defined many galaxies soften. Stars gradually redistribute into broader, more diffuse shapes. Over immense spans of time, galaxies begin to resemble great elliptical clouds of faint stellar remnants. Their structure becomes less defined, less sharply drawn. Edges blur, contrast fades. The universe does not erase its structures. It gently smooths them. And yet, even in this fading, there is continuity. The gravitational bonds that hold galaxies together remain strong for an extraordinarily long time. Stars continue orbiting, even as the light that once defined their neighborhoods diminishes. Gravity, once again, is the quiet custodian of structure. It preserves what light can no longer emphasize. Meanwhile, the expansion of the universe continues its patient work, gradually increasing the distances between galaxy clusters that are not gravitationally bound. In regions far from local groups, galaxies drift into isolation, each becoming an island of matter surrounded by an ever-expanding ocean of darkness. From within those future galaxies, the universe would appear dramatically different from what we see today. Fewer external reference points would be visible. The cosmic background of distant galaxies would fade. Only the local structure would remain observable. Astronomy itself would become more introspective, focused on the internal dynamics of a single galaxy rather than the large-scale structure of the cosmos. It is a reminder that knowledge is always shaped by position. Where one stands in the universe determines what can be known. And yet, even in such isolated futures, the fundamental laws of physics remain unchanged. Light still travels at the same speed. Gravity still governs motion. Particles still obey the same quantum rules that shape atoms and stars today. The stage changes. The rules do not. Somewhere in this deep future, long after the last conventional stars have ceased to form, occasional new sources of light may still appear through rare and dramatic events. Collisions between stellar remnants or the slow inspiral of compact objects can briefly release energy into the surrounding darkness. These events would be rare, but not impossible. Even in an aged universe, interactions never fully cease. Time ensures that given enough duration, even the most unlikely encounters eventually occur. Yet between those rare moments, long stretches of silence dominate. Not silence in the sense of absence of activity, but silence in the sense of equilibrium. A universe settling into balance, temperature differences becoming smaller, energy dispersing more evenly, motion continuing, but with less dramatic contrast. In this way, the cosmos gradually approaches a state where change still exists, but becomes increasingly subtle. The stars do not so much end as they slowly withdraw from prominence. Their story becomes less about creation and more about endurance, less about brilliance and more about persistence. And throughout all of this, the fundamental fabric of space continues its quiet expansion, carrying distant regions farther apart while allowing local structures to remain gently bound. It is a slow and graceful drift, as if the universe is gradually making more room for itself, one moment at a time. There is no urgency in it, no destination that demands arrival, only continuation, only the steady unfolding of time across scales so vast that even the most patient imagination finds itself resting comfortably within them. As the cosmos proceeds through its long, unbroken rhythm of becoming, transforming, and quietly enduring. As the deepest reaches of cosmic time continue to unfold, the universe enters a stage where even transformation becomes increasingly rare. It is not that change stops entirely, but rather that the intervals between meaningful events stretch further and further apart, until vast stretches of space and time seem to rest in a kind of gentle equilibrium. In this far future, galaxies that remain gravitationally bound slowly settle into quiet configurations. Their stars, long past the era of active formation, continue their orbits with a calm regularity that would feel almost timeless to any observer. Without the bright blue glow of newborn stars, these galaxies take on softer hues, dominated by the faint light of aging stellar remnants. White dwarfs still glow, though only faintly. Neutron stars remain present, though largely invisible except through their gravitational influence. Black holes persist, their presence marked more by the motion of nearby objects than by any visible light. It is a universe that has not become empty, but one that has become subdued. The distinction is important. Emptiness suggests absence. Subtlety suggests presence without emphasis. And in this era, the universe is still very much present. It simply speaks in quieter ways. One of the most profound transitions during this distant epoch is the near-complete exhaustion of easily accessible energy sources. Stars once acted as vast engines, steadily converting mass into radiation over billions of years. With their decline, the cosmos loses much of its dynamic brightness. Yet energy itself is never destroyed. It only changes form, heat spreads, radiation disperses, matter settles into deeper gravitational wells. Over immense timescales, the universe moves toward a more uniform distribution of energy, where differences in temperature and density become increasingly subtle. Physicists sometimes refer to this trend as the approach toward thermodynamic equilibrium. It is not a sudden state, but a gradual tendency, a direction rather than a destination. In such a universe, work becomes more difficult to extract. Differences that once powered stars, winds, oceans, and chemical reactions slowly diminish. Everything continues to exist, but with fewer contrasts to drive large-scale activity. Still, even here, pockets of complexity remain for a time. Black holes, for example, continue to act as long-lived reservoirs of extreme gravity. Matter that drifts too close does not simply disappear instantly, but instead forms accretion structures, heating and radiating energy before crossing the point of no return. These processes, though rare in this era, still provide brief moments of brightness in an otherwise dim cosmos. They are like distant echoes of a once more active universe. Meanwhile, isolated stellar remnants continue their slow evolution. White dwarfs, cooling steadily, eventually reach temperatures so low that their radiation becomes negligible. At that stage, they are often referred to as black dwarfs. Though this remains a theoretical concept because the universe has not yet existed long enough for any to fully form. They represent a future still waiting to arrive, a reminder that even in its most distant phases, the universe is not finished with its possibilities. Some structures persist far longer than others simply because of the stability of their configurations. Gravitationally bound systems, such as remnants of galaxies or tightly bound clusters, may remain intact for extraordinarily long periods. Their internal motions continue, orbit after orbit, with little external influence to disturb them. To an observer embedded within such a structure, time might still feel structured and familiar. Stars, or their remnants, would still trace predictable paths. Nights would still pass in cycles, even if the sources of light were far dimmer than in earlier eras. But beyond these islands of stability, the expansion of the universe continues its quiet separation of distant regions. Space itself stretches, carrying unbound structures farther apart until they drift beyond each other's observable reach. In this way, the universe becomes increasingly compartmentalized, not fragmented in a violent sense, but gently partitioned by distance. Each gravitationally bound system becomes its own long-lived enclave of matter and energy, surrounded by ever-growing expanses of near-empty space. Over time, communication between these regions becomes impossible, not because signals cease to exist, but because space expands faster than those signals can bridge the gap. It is a slow form of isolation, unfolding so gradually that it would be imperceptible over almost any conceivable span of observation. And yet, from the perspective of the deepest future, it becomes one of the defining features of cosmic structure. Even so, within these isolated regions, complexity does not vanish immediately. Gravitational interactions continue shaping orbits. Occasional collisions between compact objects still occur. Rare events briefly release bursts of energy, momentarily illuminating otherwise dark regions. But each of these events becomes increasingly separated by vast periods of quiet. It is as though the universe is exhaling slowly, with longer and longer pauses between breaths. At this stage, one of the most enduring sources of activity is black hole evaporation. Through the subtle process predicted by quantum theory, black holes emit extremely faint radiation over inconceivably long timescales. As they do so, they gradually lose mass, shrinking ever so slightly as the ages pass. For most black holes, this process is effectively invisible for nearly all of cosmic history. Only in the most distant future does it become the dominant mechanism of change. And even then, it is extraordinarily slow. A black hole does not vanish in an instant. It fades, gradually, patiently, until, at the end of an almost unimaginable duration, it releases its final energy in a very faint and brief burst before disappearing entirely. That moment, however, belongs to an era so far removed from anything we experience today that it feels almost abstract. Yet it is still part of the same continuous story. The same laws of physics that govern falling rain and orbiting planets also govern that final evaporation. There is a remarkable unity in that continuity. From the earliest moments after the universe began to the distant future where black holes slowly fade, the same principles remain in place. Expansion, gravity, thermodynamics, quantum mechanics. They persist without interruption, guiding the evolution of everything from the smallest particles to the largest cosmic structures. And through all of it, the universe remains patient. It does not rush toward endings. It does not hurry toward conclusions. It unfolds at the pace that its own laws allow. Even as light becomes rarer, and energy differences become smaller, and structures grow more isolated, the universe continues to exist in a state of ongoing transformation. Not static, not finished, but quietly evolving, like a vast ocean at night where the surface appears still, yet beneath it currents continue to move with slow and persistent grace. And in that deep stillness, across unimaginable spans of time, the cosmos continues its long and gentle passage forward, carrying every remaining atom, every fading glow, and every silent black hole through a future that stretches onward without urgency, without interruption, and without end that can yet be seen.